Hello everyone, this JSON was generated by quantized LLM which I fine-tuned in Google Colab itself. And I'm going to share to you all about the trick of how I fine-tuned an LLM to generate such a good JSON response, because as you can see here, the JSON response is pretty accurate. So stay till the end to know everything about how you can trick the model to do this task. Let me see the use case. The idea is that the user will stop his conversation at some point of time, and the model should be able to understand the intent of the user and then respond accordingly, like in this use case, because he has tried in some specific restaurant, it seems. All right, so it will see, okay, you have these conditions. So for example, here it should have burgers in its cuisine and it should serve alcohol. All right, and the city should be San Francisco. All right, and the user is requesting alternate restaurants. So the action for the model is to generate alternative restaurants which has these things. Okay, so it is kind of an extraction first and generating some response based on it. Okay, so here you can see that the model is saying there is a nice Mexican mole restaurant in San Francisco. This JSON output was generated by the model, but I didn't train the model to generate JSON directly. That's why I said I tricked the model into generating a JSON structure, because I did the fine tuning with XML format. Okay, so now I'm going to share you all about the trick. So let's go into the code, and while going through the code, I'll also share to you about the trick what I used. All right, so here first we need to install some dependencies. Based on this code itself, if you train, you will get an error known as there is an in place error with leaf variable. Okay, I'll show you how you can handle it in Google Colab itself, because it requires a modification in the library. Let's run that. Next, we are doing some imports, where we are doing import of transformers, and then we are importing LoRa config, pef model, get pef model, and prepare model for k-bit training. So in transformers, we are importing auto model for causal LLM, auto tokenizer, training arguments, trainer, default data collator. Okay, these are all some imports there. And here we are importing torch. We are having data class, field, and some other imports. All right, so here we have data loader and all. So let's import that also. But here is where the trick starts actually. The thing is, in the data set, let me show the data set first, and then you will understand what is the trick. All right, so thanks to this guy, I think his name is Saurabh Mangalur. He has released this amazing dataset which was very useful for this video. Right, the idea is that he'll have this kind of thing, like for example, I'm feeling hungry, I would like to find a place to eat. So it will ask, do you have a specific location where you want to eat, something like that. It will try to generate where it will find the intent, and then it will try to provide an action for it. Okay, so the thing is, here let's say I'm doing a tokenization of this, right? What happens is, this begin target, let's say inside begin target it is like AB. Okay, it will be like this. Usually the tokenizers won't have these as single tokens. So what will happen is, it will tokenize like this: token 1, 2, 3, 4, 5, 6. We can consider this to be one token because the entity is always going to be the same. But what happens is, it will be 6 tokens. Now the disadvantage is that the model needs to know the order of the 6 token. Let's say it is 1, 2, 5, 8, 7, 6. Okay, it should always generate 1, 2, 5, 8, 7, 6 continuously. Hard to generate such a continuous equation. So what happens is it will do something like this. A, B, this will be okay. Like it will be go like this. So we can't parse it. We can't write any logic, right? So this is the first problem. Okay, let me write it as hard to generate structure, which is why even we are facing the same in JSON, right? And that is what we are going to solve now. Okay, for JSON, the problem is that you need to keep a structure like this, and there will be tab spaces. And if you don't maintain consistent tabs, then you're going to make some problems in there. All right. And that's why we are going to go into a format known as XML. For people who are wondering how XML will be, it is like almost similar to HTML tags, right? But it is like JSON written in a HTML format. So let's say JSON is like this: A is to 1, B is to 2, and this value is A. So let's say C. Okay, it will be C opened inside A. It will be 1 and then closed A, B open 2, closed B, and then C will be closed. All right. So this is how XML works, and it is interchangeable. Okay. And here also you can wonder, wasn't still it is going to be 1, 2, 3 tokens, right? And that is where our trick come into the picture. Okay. Now is where I'm gonna reveal the real capability of how the model was able to generate such a structured JSON, because you can always parse this XML to JSON. How it happens? See, like without this trick, what will happen is, let's say it is like a complex structure B1 slash B C2, it will do like this. Okay, instead of putting the slash here, it will put here. It won't parse. It will say XML is wrong. Okay, so now what we are going to do is, here we know the entities before, right? Let's say you are doing some extraction, you always know the entities. So let's say you are doing some receipt extraction, you want to get probably the store name, the amount, and then probably the address. Okay, you will create 3 tokens for it first. Okay, store, address, and then maybe the mobile number. Okay, mobile number. And you'll do the same here. Okay, you'll close those. So it will replicate. Okay, and what we'll do here is, this is where the real trick is. We'll add these tokens one by one, 4, 5, 6, into the vocabulary of tokenizer. Okay, that is the real trick. We'll be adding these to the tokenizer, and you will face a lot of errors after that also. So I'll say that later how you can solve those. But the first thing is to avoid this problem of having incompatible structures, like doing this, or having open tags but no close tags. All these problems can be done or solved with the help of adding these tokens to the vocabulary. Okay, and next what you will need to do, you need to write a function which will convert XML into JSON, and that is how you will make your model to generate a JSON output without even the model knows that it is a JSON. Okay, so now that that is clear, let me continue with the code. All right, so here you can see there is no XML format in here, right? There is some format, yes, but the XML format is not there. Okay, and why I'm keeping XML is that this might suit for this use case, but for other use case you will require XML. Like I can directly add these tokens into the vocabulary and it will work, but I'm not doing it for that. You guys should be able to use this for any of your information extraction use case. Yes, you heard it right. You can use this code itself for any of your information extraction use case for fine tuning any model for it. Okay, all you need to do is like don't even consider this function. That's all. Okay, once you create this class, you'll be done. Don't worry, I'm going to explain now each of those. Okay, so the first thing is I'm converting these tags to XML tags. Okay, so if it is like this begin, it will be like target, and if it is end, I'll end, close it. Okay, similarly I did for all the tokens, and here we are creating a class known as special tokens. You can have it as any name. I kept it as special tokens because we are adding these as special tokens to the tokenizer. All right, and all I did was I have all of these in the token name. Okay, except that in BOS token I had it as start of text. You can also have it as S. Okay, it's upon your choice. That's all. Okay, like after that there is nothing for you to worry about. Next, what you need to do is obviously you need to have a class method here where what it will do is it will take these values and provide it as list. If you do that, your first step is over, which is to have the set of entities which you are going to extract. All right, so next what we are doing is, so let me run these. We are importing the data set. I'm doing a train test split because we need to test the model, right? So I'm doing a train test split and I'm providing the column name because it has a column name as target, but we are going to modify the target, right? Here you can see, right, we are modifying it from here to here. Here you can see target becomes new target. Okay, so I'm giving the column of label to be new target, and then we are applying a function to the dataset, which is to replace with XML tags. Okay, this function is called. So what it does is it will go only to the target. I didn't do this for source because I know the model will be able to learn the tags, but to generate it, it is very hard. So I'm not changing anything, but if you change, it should improve the performance, not decrease the performance. Okay, here you can see I'm having a dictionary known as model input, where token input is your batch. Okay, and inside that I'm taking the target alone as a token, and I'm doing all the replacing, where in model input I'm providing the context to be context, target to be target, and new target to be the list of this value. Okay, so that is what is the first step. Have your data set in the XML format. If you are doing it in JSON, you need to convert that JSON to XML. All right, so if you want a video on how you want to convert a JSON to XML, because in this video I'll show you how you can convert an XML to JSON. That I'm going to show you today. Okay, but if you want to know this first step of how I can convert any JSON to XML, let me know. I'll make a short video or probably make a YouTube shorts for it of how you can convert a JSON into XML. All right, so that you will be ready. That is your first step. And then the second step for you would be to tokenize it. All right, obviously you have your data, you need to tokenize it. But the thing is, you're going to see a difference now. If I do a length of the tokenizer, usually you'll get the vocab size. All right, so I'm doing len of tokenizer, and here if you see it would be 32,000. Okay, and this is where the third part comes into the picture, because now it is going to change from 32,000 to 32,027 because we added 27 tokens. If you count this list of tokens, it will be 27. Okay, so what I'm doing here, you can see I'm specifying that the pad token should be pad token, which we have provided here as pad, and then I'm stating the BOS token is the BOS token, and end token is the end target token, which all are provided there. And for additional special tokens, please do refer on to special tokens, not list. That's what we are calling. That's why we had this. All right, these are all our special tokens. All right, so if you prepare your data to XML, the first step for you would be to create this class called special tokens, and that is when you can move on to the next step. All right, so now the thing is, if you fine tune this model, right, you will get into an error where it will say like it is list index out of error, because vocab size is going above the dimension of 32,000, because the embedding dimension of the model is 32,000, not 32,027. 32,000 comma some hidden dimension, embedding dimension. All right, but the vocab size is 32,000. So now coming on to the second part of the trick, which is to resize the token embedding. There is a function called resize token embeddings, which will change the dimension of the model's embedding, and we are setting it to be this value from 32,000. Okay, so that is the next step. I'm just calling the model and I'm saying that I need to load it in 4-bit. All right, and let it load. Let me go on to the next steps. The third important part of the trick here, when you are changing the tokens, right, of the tokenizer, your embedding layer and your feed forward layers and all won't have a clue, especially your embedding layer won't have a clue about the new tokens. So when you're training it with LoRa, make sure that you are having the embedding tokens as well as LM head to be in your target modules. Okay, rest are dependent on the model and your choice, but find what are the target modules which are related to embedding. Okay, which would be mostly embedding tokens and LM head, and probably yeah, like based on the model it will vary, but make sure that that two modules are there in your target model. That is the third part of the trick. The first part of the trick is to convert your model into an XML and have all the XML tags you created in a special class. The next step of the trick is to add those in a tokenizer and then resize the token embedding of the model to the length of the tokenizer you created by adding these. The third step of the trick is to have this embedding dimension and LM head. Okay, that is the third step of the trick. The next step would be to prepare the dataset. We are doing some tokenization here, tokenizing the data now. So I hope you all know what is tokenization. And I'm just checking here if the dataset is there. And as you can see, there is tokenization, and 32,002 is nothing but your pad token. Okay, if you want to check, you can check it. All right. So next is our dataset is ready. So we'll create a data loader. Okay, so now you have your data loader, you have your model, creating the training arguments as usual, and I'm providing the number of training epochs. You can give 3 also, and then I'm providing the batch size, warm-up steps, after how long the back propagation should start. For example, here I'm saying after 10 steps only the back propagation should start. All right, and then I'm saying weight decay is 0.0001 when scheduler optimizes the learning rate, like it will change the learning rate, right? It will have a weight decay of 0.0001. And then I'm saying like I'm gonna train in mixed expression, so FP16 is true, logging steps is 10, so that at every 10 step I'll have training loss being logged. Learning rate is 1e minus 5, that is the maximum learning rate the model can attain, sorry, the training loop can go up to. And then this is to avoid a warning, that's all. Okay, use reintent equal to is to false. And then I'm also saying the hub model ID wasn't intent recognition, and I'm gonna push it to the hub. If you think that okay, Vasant, I'm doing an enterprise use case, because purposely I had hub private repo equal to true being commented there, because when you're seeing this video, most people will do this because you might need in your company. Okay, and you might find it hard to have it as a public model, and you don't want to like push it in public even for a second. So at the time what you can do is uncomment this thing, hub private repo to true, so that it will be a private repo even while it is uploading. You need not go and then change in hub and out. All right, so next we have a trainer which will take these training arguments, data set, model, and then the data collator, which is default data collator. And like I said, you got this error. A leaf variable that requires grad is being used in an in-place operation. This is a very common error, guys. You might face this in loss functions as well. And I'm going to show you all how you can rectify these kind of errors. Here the problem with this error is that when you do an in place operation, right, the in place operation means a variable equal to a variable plus some variable itself gets replaced. If there is a gradient involved in that variable, that is when the problem happens. Okay, and now we are going to just do some hack added two lines and this would work. But for that, what you need to do is first restart the runtime, but don't install the packages again because just now we have changed the package. All right, you need to restart the runtime and again run all of those. And now you can see the training has started, right? It is showing 1 hour. I'm not gonna run it, I'm gonna cut in front of you itself. You can train it for longer time and then run this cell, okay, so that it will push your adapters which you have trained right now, the LoRa adapters, it will be pushed into hub. And for normal inference you can follow this. And if you think, okay Vasant, I'm not into like normal inference, I want to do it in an application level, okay, don't worry, I got you. The first thing, which is probably this is the last trick, okay, this is the last part of the trick, because now you need to convert this XML to JSON. For that you'll use a library known as XML to dict. All right, so in that there is a function called parse which will have a specific function behind that which will parse this XML into a JSON. All right, so here the thing is you're calling the model, okay, you should also resize the token embeddings again. All right, you should call the model, you should resize the token embeddings again. You should not call it as peft model for causal LLM how I used to call it always, because when you do auto peft model for causal LLM, it won't do this resize token embeddings call, and then it will give an error. Okay, so you should call it this way: call the model, resize the token embeddings, and then attach your adapters like this, and then yeah, like set it to CUDA. All right, and then next what you need to do is have the inputs ready, send it to the inference model which we created right now, and then yeah, get the output. And here I just replace the context because this is a completion, like it will try to complete from the context, right? So I replace the context and all, and then I'm sending that string onto the XML string to JSON string function which showed you here, right, which will convert the XML to dictionary. And then yeah, finally you will get a result how we got in here. For this application we are going to use a simple yet powerful library known as Gradio. For rapid prototyping, Gradio is good. And the best part is, if you have a Colab Pro notebook, right, if you start an instance here, there you can send this URL to people, and then yeah, they will also be able to use your application for free. Yeah, that's the good part. All right, so here I'm calling the gr.interface function, okay, in which I'm calling the get response function, which will take input as text and then it will return a JSON output. That is what it is. And then you need to call the launch function of demo. And as you can see, here we got the response. And now it is saying some A16 restaurant is a nice restaurant in San Francisco. And now the very important thing is you need to see how really the output will look like before you parse it. Okay, that is very important for you all to know. I'm going to show you that. So here you can see this is the target starting. All right. And here is where the target starts. Target, DSTS, DST. Inside that, there is intent, which is to find restaurant. And then I'm closing the intent. The belief is that in the city of San Francisco, the restaurants are to be found where the cuisine is having burgers and the restaurant serves alcohol. Okay, so that should be true. That is the belief of the model. And next, it is saying that the user action is to find alternate restaurants. And then now my action is to offer him a restaurant name known as A16 restaurant, which is in San Francisco. Okay, so he's saying like A16 restaurant is a nice restaurant in San Francisco. So it is closing its response and it is closing its target. And that is how you fool your model or trick your model into generating a JSON without even the model knowing that it is trying to generate a JSON structure output. So yeah guys, I hope you all like this video. If you all like this video, please hit the like button. Or even if you think, okay, I got some knowledge in this video, please hit the like button and share it with your friends and communities so that they will also be able to make their model to generate JSON. See you all in the next video. Until then, cheers.